Hello and welcome back to Basic Topology, the video series where we talk about topological spaces and how we can use them in analysis. And indeed, in today's part 4, we will talk about the general definition of compact sets. However, as always, before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as you might already know, you can use the link in the description to download a lot of additional material for the videos. And with that out of the way, I would say we can immediately start, and the topic of today is compactness. This is a really important notion that occurs a lot in mathematics, and you might have already seen it in the real analysis course. And when we talk about a compact set, a good way to remember it is to say that a compact set is close to a finite set. So it can definitely be finite, but if it's infinite, it's the smallest possible step to infinity in some sense. But here it's really important to note that we don't measure this infinity in the set theoretic sense, but in our topological sense. In other words, when we say compact, it's always with respect to a given topology. So for example, you might know that on the real number line, the sets that are closed and bounded are exactly the compact sets. And this is with respect to the standard topology on the real number line and something that does not hold in general. This means in a general topological space Xt, we need a new and precise definition what compact sets actually are. So the question is, what is the criterion that a given set A as a subset of X is compact? So maybe let's visualize A like that. And now the notion compact can be visualized by covering the whole set A with open sets. So these sets come from our topology T and they can be big or small, it does not matter. The only thing we want is that we cover the whole set A. And now of course by going smaller and smaller, it could definitely happen that we have infinitely many open sets involved. So maybe there are a lot of possibilities, but it's clear that we can always find at least one such covering. Moreover, it's also clear that for a finite set, we can reduce a given cover a lot. For example, if A only consists of 5 elements, then 5 of these open sets should be enough to cover the whole set. So even in the case that there are infinitely many sets given in this cover, we can always choose a finite subcover. In other words, here you can skip a lot of these open sets, such that only finitely many remain that still cover the whole set. So this is not so surprising for a finite set, but for an infinite one, this is exactly what we would call compact. Hence, now we can already formulate the general definition. And as already mentioned, this is the definition we have in topological spaces, because there are also some other ones you can use if the space has some more structure. For example, in the functional analysis course, we could give a sequence description because we had a metric space given. But as we will see soon, this is just a special case of this general definition. So now let's write it down. We call a subset A in X compact if any open cover of A has a finite subcover. This is the short description you definitely should remember, but now we can write it down in a precise way. So what we need is just a collection of open sets, so sets from T. And maybe let's call these open sets UI. And now we have a whole collection, which means we have an index set capital I given. So this is just a collection of open sets, and now the requirement is that they cover the set A. So the union of all the sets UI is equal or larger than A. So in fact, this is what we mean by a cover of the set A. And now we call the set compact if we only need finitely many members of this collection of open sets to get a cover. This means we can reduce the index set to a finite index set I0. And then we just have to take this finite union of the open sets. But with that we don't change the property that the union is still a superset of A. And here the crucial thing to remember is that we only have compactness if this implication is true for any collection of open sets. So there we have it. This is the definition you should remember, and we immediately see that finite sets are definitely compact. Therefore, it's definitely more interesting to look at some infinite sets that are compact. And maybe let's keep it simple. Let's take the real number line R with the standard topology on it. And the first subset we consider here is the space itself. So let's simply try to cover R with some open sets. So for example, we could take the open intervals from -n to +n. And then we just go with n through the whole natural numbers. This clearly hits every real number, so we have an open cover. But we also immediately see that finitely many of these open sets are not enough. Hence, for this choice of an open cover, there is no finite subcover. So the conclusion here is that R, together with the standard topology, is not a compact set. On the other hand, we definitely have compact sets, for example the unit interval from 0 to 1. This, as a subset in our topological space, is compact. Indeed, we already know that every closed and bounded subset of R is a compact set. However, let's start proving this fact for this nice simple interval from 0 to 1. So what we have to do is to show that every open cover has a finite subcover. This means we just fix such an open cover for the whole interval. So in general, we know that we have infinitely many open sets Ui. And now one nice idea for the proof is just to take a point from the interval and check if the subinterval here has a finite subcover. So this defines a whole set of points where a finite subcover exists. To keep it simple, let's call this set S and let's put all the points x in. So x lies between 0 and 1, and we want that the interval from 0 to x has a finite subcover. And at this point you already know, this just means that we only need finitely many sets Ui that cover the whole interval. And the common way to do that is to write I in I0, where I0 is a finite subset of our index set I. Okay, and now by the definition of S, we immediately see that the supremum of S is definitely not larger than 1. And actually, we want to show it's exactly given as 1. But at the moment, we only know that this supremum lies between 0 and 1. In fact, we know that 0 lies in the set S, because the interval from 0 to 0 is a finite set, and a finite set is always compact. Therefore, in the first step here, let's show that we have even more elements in S. And for example, we can just look at the point 0, and we know it lies in an open set. Let's simply say this is the set Ui1 from our covering. And since it's an open set in the standard topology, we know that every point inside has an epsilon ball around it. Hence, for our point 0 here, we could say that from -epsilon to +epsilon, we have a subset in Ui1. So you see, we only need one open set from the whole covering to describe a neighborhood around the origin. And this also implies that we can easily go to a closed interval inside the epsilon neighborhood. So for example, we could just do that by taking epsilon ½ instead of epsilon. Therefore, we get that 0 to epsilon ½ lies completely in the open set Ui1. So it's just a single open set, so definitely a finite subcover for this interval. Therefore, this epsilon ½ which is non-zero, also lies in our set S. And this yields that our supremum is strictly greater than 0. So we are one step further to showing that the supremum of S is given by 1. But at the moment we just know that there is a positive distance from 0. And now we can use the same reasoning as before, because we know that the supremum lies in an open set from the covering. So let's simply call this one Ui2. And indeed, as before, we can use that by definition of the standard topology, we know that there is an epsilon ball in it. Of course, the actual value of this epsilon might be different than before, but we know that such a positive constant exists. And now we can use this nice epsilon neighborhood to choose a point to the left of the supremum. And in order to keep it simple, let's simply call this point x tilde. And moreover, what we also get is that the closed interval from x tilde to the supremum of S lies completely in our open set UI2. So as before, this closed interval here is covered by a single open set. And with that information, we can just look at the whole interval from 0 to the supremum of S. Because this one we can just split up at x tilde. So we have 0 to x tilde union x tilde to the supremum of S. And for the last one, we already know it's covered by a single open set. On the other hand, for the first interval, we already know it has a finite subcover because x tilde is smaller than the supremum of S. So this simply means that x tilde has to lie inside the set S, so this interval has a finite subcover. So in total we get that our interval from 0 to the supremum of S also has a finite subcover, which simply implies that the supremum of S is an element of S as well. And please note, this is new information because in general the supremum of a set does not have to lie in the set itself. Okay, and now for the last step of the proof, let's do a proof by contradiction and let's assume that the supremum of S is not equal to 1. In other words, let's look what happens when we assume that the supremum of S is strictly less than 1. And there we can use the same picture as before because UI2 is an open set around the point supremum of S. However, now of course it could happen that this point 1 lies inside this epsilon neighborhood. However, in any case, it's always possible for us to find a point between the supremum of S and 1 that lies inside this epsilon neighborhood. And let's simply say that we can find this point with a little delta greater than 0. This simply means that we have the interval that starts with the supremum of S and goes to the supremum of S plus delta. And now if delta is small enough, we lie completely inside the open set UI2. And there you should see, we can do exactly the same thing we did before. We can just form the union of two intervals and we see we have a finite subcover for both. In fact, it's the same reasoning as before. The second set is covered by a single open set and the other one has a finite subcover. However, now the conclusion here is that the supremum S plus delta also lies in the set S. And exactly this is the contradiction because this number here is larger than the supremum of S. And of course this cannot be by the definition of the supremum. And by this contradiction we see that the supremum of our set S has to be equal to 1. And that finishes our proof. We have shown that the unit interval in R is compact. So maybe this was not so surprising for you. Therefore I would say let's look at some other topological spaces with compact sets in the next videos. So I hope I meet you there again and have a nice day. Bye bye.